assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we're going to figure out what the induced EMF is in this loop of wire here in a constant uniform magnetic field. When we take it from this square loop configuration here, and then we just squish it down to where it looks something like this, where basically we've gotten rid of all the area in our loop. So that's really going to be the key thing to realize in this problem, is that we go from having an area of a square in the first situation here. So initially we have an area of width times length, 0.25 meters times 0.35 meters, and we end up with effectively no area. Or it's small enough to where we can say it's basically zero. Okay. So to actually solve for our induced EMF, we're just going to recall that Faraday's law of induction states that the induced EMF in our wire here is going to be equal to minus the change in the magnetic flux over the change in time. Where our change in flux is just going to be our final flux minus our initial flux. And our change in time is just given right there as 0.18 seconds. We'll just leave it as delta t for now. Okay. So our equation for the magnetic flux through this loop in general is just going to be B times A times the cosine of the angle between the surface normal and the magnetic field. And of course, we know that our surface normal and our magnetic field are going to be parallel to each other, which means that theta is 0 and the cosine of 0 is 1. So our flux is just B times A. And in our second situation here, where we flattened out our wire, we're saying that our area is effectively 0. So that's just going to mean that the flux in the second situation here is going to be 0. So since A final is 0, we're saying the flux is 0. So we can just zero that out right away, and then plug in our expression for the initial flux here. So we'll have minus the initial flux, which will be just plus E times the initial area. So we'll have B times our initial area divided by delta T. All right. So now, given that we have our strength of our magnetic field there, the time interval and our initial area, just right over here, we are ready to just plug these values in. And if we do that, we will get that our induced EMF comes out to be 0.25 volts. So that is how you would calculate the induced EMF in a loop in a uniform constant magnetic field, where we start off with this square loop and we flatten it out so that there's virtually no area left in our loop.